Alrighty, right. So some of y'all were confused about some of the math that we did today. I was just going to go back over a couple of the math problems again for super duper clarification purposes, so we're all on the same page. These are going to be number 2 and 3 in your soil moisture problems part 1. So that's what we're covering. All right, so for number 2, we are asked, what is the oven dry mass of a 560 gram soil sample containing 25% water by mass? So 25% water by mass is that theta G we talked about, or some of you were telling me Chip writes it theta M. So that is the water content by mass, and that's what we covered a little bit on the board today, and that is going to be one of our givens here, so that's important to consider. And then the other given we are given is the 560 grams of soil, and that is not oven dry soil, right? So that would be the mass wet, and that's another one of our givens. So those two givens we are given is theta G, and we are also given M sub wet, right? Awesome. I think it's super helpful when you have math to identify what your givens are as a way of figuring out what equation is appropriate to use. So we know our theta G equals 25% because that is the 25% water by mass, which is the gravimetric water content, right? And then the other value we have is a wet soil sample. Anything that's not oven dry is wet. So it could be air dry and be considered wet, or it could be saturated, whatever. Cool. So that is M sub wet. And that is equal to 560 grams. Cool. So given that information, hopefully you can see it somewhat okay. We're going to do a little bit of math, and we have an equation for that, which I gave in class. A couple equations, right? So you can find the oven dry here, or you could plug into this one and do a little bit of algebra. I'm going to do it that way. It's the same math either way, because this is basically, we just switched what side of the problem that's on. But for me, that makes more sense in my brain, and also for like retaining that information. So we have 0.25, right? Because 25% is you need to convert to 0.25, or you're not going to get the right significant figures, etc. And that is equal to M wet, which is 560 grams minus X. I'm just going to use X because for me it's a little easier to write. And then that is all over X. And that X value here is the mass, the mass oven dry. So can we see that? Sorry, I don't have a better system for writing this, but it is what it is. So we need to multiply all of these by X, right? And that will cancel out that X. It'll put an X on that side. So that is written to 0.25. X equals 560 minus X grams, because that one canceled and we had to multiply it. Okay, so then we're going to add an X, and that's just one X, right? So we're going to add an X here, and that'll be 1.25 equals 1.25x, equals 560 grams, right? Awesome. So then we will divide by 1.25, and that'll cancel here, and then we'll just do the division in our calculator, nice and easy. 560 divided by 1.25, and there you go. 448, right? We wrote this on the board. That's just a little more clarification on how you got that information. Apologies. It is, I know, not the perfect camera angle here, but that's how you do it. The reason you do it this way, and I got this from Rebecca, who teaches the other class, is this percentage is parts per 100, not a percentage of a whole, if that makes sense, because percentages can represent different things, which I forgot about. But so it's not something where you can just multiply by 0.75. Another way she said it was just trust the older soil scientists and use the equation. So that's what we did. All right, we're going to move to the next one. All right. A uniform soil depth, keep that in mind, contains 32% water by mass. So we will indicate, okay, what is water by mass? We had that in the last one. That is our theta G value. So good to identify that variable. And has a bulk density of 1.48. So we know our bulk density, which we had in our equations as d sub little b of 1.48. We also know our bulk, our density of water, right? That's a constant. So that's dW, and we know that is 1 gram per centimeter cubed, right? So we know there's a couple ways to get the gravimetric volume content by volume, theta sub v. So there's two different ways. The first way, we need the volume of water and we need the total soil volume. Are we given that? No, we are not. Instead, we are given the bulk density, right? We have that here, the 1.48 grams per centimeter cubed, and we know the density of water. That's 1 grams per centimeter cubed, right? That doesn't change. That's a constant. And we also know our theta G, right? Because that is 32% of water by mass. That's what we had for G. So we have all of the different variables here. We have all of the variables here to calculate for theta V. So we have the theta G, that's the percentage that's in the equation, 32%. We have the bulk density that's given, and we have the bulk density of water, that's a known. So we can calculate for that one. That's the first part of the equation, and we're going to do that right now. So there I just wrote out my givens. Again, it's a good practice to do this just so you know what you're working with. That'll often answer what equation you need to use. It's just identifying what you're given and what it matches up to the equations you know and have, right? And because we identified that these are the variables we have, that's the equation we're going to use, right? Those are all the variables we have in the equation. So 0.32 is the theta G, and that is multiplied by the density of the bulk density, 1.48 grams per centimeter cubed all over 1, right? Grams per centimeter cubed for the bulk, or for the density of water, sorry. I already know those units canceled, but it is a good practice to write out your units. Those cancel. We're getting a percentage in the end, so it makes sense that there's no units because it is a percentage, right? All right, I'll let you do the calculation. I don't want to do everything for you, so you have all the tools there to do the calculation. All right, so now we are calculating the cm of water held in the top 20 cm of this soil. Now this one should be easy. It's just a plug and play with what we last did. We have the depths of the soil, right? We have the theta V. We calculated that in the last equation, and that should be a simple matter of plugging and playing, and you should get the correct answer. That way, I'm not going to do it for you, but that is the equation you need to use because that will give us the depth of the water, W, or D sub W. And that is all you need to do that one. That should give you all the answers you need and hopefully answers a lot of your questions. I know a lot of people were thrown off this, but hopefully that's all you need and you'll be good. And obviously these are the notes we did in class, so this should be what you have. It's good to have a bit of, scrap paper. Make sure you're doing all that, but my tip for you is to look at what you have in front of you. And this is what I try and do when y'all ask me questions and I have to jump back into something I was doing earlier, jumping all around, is to just look at what my variables are given and then pull, okay, that's what equation from this has those given variables. How can I figure out where I need to go based off that? And then, like I said, I'm a big fan of writing out what your variables are. That way, you know what's given. It turns a word problem less into a word problem and more into a a written problem that's a little more explanatory for you. And that's that. So hopefully that helped. I know this camera angle is less than ideal, but hopefully that helped a little bit. And let me know if you have other questions. I'll give your givens soon. And have a great weekend. Stay safe in the weather.